Check this out. This isn't a texture, and it's not a standard 3D model. This is a volumetric cloud purely calculated inside a cube using math. With the power of WebGPU, we can even run this expensive Raymarching algorithm smoothly right in the browser. I know, hearing Raymarching gives many people a headache. But today, using Three.js TSL, we're going to break this complex algorithm down into simple building blocks. Make a box, shoot some rays, sculpt the shape, and add noise. Follow along with these few lines of code, and you'll be able to turn any geometry into mist.
Let's save some time and use the RACF snippet to scaffold the component. Just swap the container tag to canvas and the imports settle themselves. For an immersive experience, the style uses absolute positioning to fill the entire screen with a black background. Focus on this DPR setting. I'm hard capping it between 1 and 1.5. Volumetric clouds are GPU killers. If you run full 3x resolution on a Retina screen, your frame rate will tank. Trading a tiny bit of sharpness for a smooth FPS is an absolute must-make deal. Crucial step: initializing the WebGPURenderer. This is the prerequisite for playing with TSL. While we're at it, set the output color space to sRGB. Otherwise, your final render will look washed out, a detail that's easily missed. Next, let's define the FoggyBox component. Watch this line. Wrap the material build function inside useMemo. TSL is essentially building a massive node graph. If you write this directly in the render loop, React will rebuild the entire shader logic on every re-render, which is an absolute performance disaster. So we must ensure this complex material is only compiled once at initialization.
Now we've placed a 2x2x2 fish tank in the scene. All the clouds and fog we create later will be confined inside this box. Entering Build Foggy Material. We simply knew a Mesh Basic Node material. Two pitfalls here. First, side must be double side or it disappears when you fly inside the box. Second, depth right must be false. Since this is a transparent object, keeping depth right on will cause weird occlusion issues. Then, wrap our main logic with TSL's fn. Let's return red for now and bind it to matte.color node, just to test if the pipeline is working. Now, entering the core math zone. Don't panic, look at the diagram. We need to calculate the direction of each ray, RD. The formula is simple. Target position minus camera position. Finally, use normalize to standardize it, ensuring it only represents direction with a length of 1. Next, determine the launch point, ray origin. There's a smart logic here. Use front-facing. If you're looking at the front, you're outside. So start at the box surface position world. But once you step inside the box, seeing the back face, the start point must instantly switch to camera position. Otherwise, the cloud vanishes the moment you enter. Here is a rookie death trap in TSL. Mutable variables must be wrapped in var. If you just write let p equals start pause, the shader treats it as a constant and you can't modify it later. So remember to put the var vest on both coordinate p and density accumule. Start the engine. Loop 12 times. This represents our sample count. The core action is this add assign. Move the probe P along the ray direction RD, marching forward 0.25 meters each time. This is Raymarching.
probing the space's density step by step. Step 1. Measure distance. Here's a trick. We use length squared instead of length. Square root calculations are expensive, and we only need to relatively compare. Save performance wherever you can. Next, define the sphere density. Look closely at the smooth step parameters. I wrote them backwards, 1.0 to 0.0. This means the closer to the center, 0, the higher the density, 1. The further away, the lower the density. Finally, add the calculated density to density accum, multiplied by 0.2 to control the thickness. Moment of truth. Change the color from debug red to pure white, vector 3 of 1.0. The most critical step. Use our accumulated density, D, to directly control the alpha transparency. Look, that rigid red box is gone, replaced with a soft-edged, glowing white object. Notice the texture, brightest in the center, fading at the edges. This is the prototype of volumetric rendering.
Now we want to shoot a beam of light into this fog. First, we don't move the object, we move the coordinate system. Use sub to offset, then rotate to spin the axes. It's like tilting the entire universe, determining the angle at which the beam cuts through. Here's the key. If we only calculate the XZ axis, it's an infinitely long pole. For a natural look, use abs of p.y for height, then multiply by a smooth step so the beam fades out at the top and bottom. Now it looks like focused energy, not a rigid stick. Finally, use the max function to fuse the sphere and the beam. Remember to update the accumulation target in the loop to this new total shape. Check the preview. The beam has visibly pierced through. But look closely. It resembles a blurred white plaster cast, rigid and monotonous. We have the geometry, but it completely lacks the soul of flowing gas. The cloud looks too plastic right now. We need noise to break it up. Prep the data. Use time to create flow, then call mx fractal noise float. Note this 1.7. It determines the fluffiness of the cloud.
Next, call mx_fractal noise float. Note that the screen will not change yet, and that's totally normal. Don't panic. We just mixed the paint, but we haven't thrown it onto the canvas.
Critical moment. Normalize the noise to a 0-1 range. Then use it to erode our original geometry, total shape. Look, just that one line of code. The rigid geometry instantly shattered, transforming into a flowing, realistic, volumetric cloud with rich internal details. That's the magic of math shaders. Look closely at the screen. Do you see those ugly tree ring banding artifacts? That's because for performance, we only sampled 12 times. The gaps between steps are too big, exposing the trick. Is there a free optimization fix? Yes. This is what we call dithering. The logic is simple. Use screen UV to generate a random number, then randomize the starting point of every pixel. The offset never exceeds one step size, 0.25. Look, instantly gone. Even though the sample count is still 12, because every pixel starts differently, the error is converted into noise, which the human eye automatically smooths out. This is the ultimate graphic trick for trading low cost for high quality. Time to color. Reminder again, you must use let to declare this. Do not write const because we are about to layer on lighting. We use density, D, as our palette. Thin areas get pale gray blue, Dense areas get deep ocean blue. This sets a cold, crisp tone for the cloud. The cloud has color now, but it's still flat. We need to add some light to the thickest parts. Here, we use POW of D to 4.0. Note, we don't want blinding white light, but translucency. The fourth power restricts the highlight to the absolute core of the cloud, making it look like it holds energy inside. Look at that texture. It completely changed. It's no longer that rigid white fog, but a deep blue nebula floating in deep space. Notice those subtle glowing details inside. That's the unique depth of volumetric rendering. If we want to dye that single light beam green, we have to extract it from the hole. We create a new pillar acume outside to track it separately. When calculating beam ratio, here's a life-saving detail. The denominator must be max total shape 0.001. Never divide by 0 directly. Otherwise, in empty areas, the shader will calculate NaN, causing black holes in your render. Last step, we need to convert that separated beam density, pillar acume, into a blend factor, P factor. Simply put, we're generating a mask to tell the GPU where to apply the second color. Use Mix to layer on this fresh mint green. Look, the once dull blue nebula is instantly pierced by this beam. This warm, cool contrast is the secret to making shaders look sophisticated and non-repetitive. Let's recap. We built a box, shot rays into it, continuously sampled the density of math shapes in a loop, and finally added noise and color. That composes the volumetric cloud we see now. WebGPU's TSL allows us to write JavaScript just like shaders, no longer needing to painfully concatenate strings. If you like this hardcore yet elegant visual effect, don't forget to hit like or go to GoodTSL to copy the source code and play around. See you in the next video.